Thank you, Oleg. So I'm Stéphane VICTORI. I'm working in Agora Lab, which is a common lab including Cimel Electronic, a French company, manufacturer for LiDAR and photometers, and LOA, a French lab based in Lille. Yeah. Our ecosystem in Agora is based on collaboration with different institutes and companies, including GRASP, Latmos, manufacturers of LiDAR system, Onera, an institution in France mainly focused on optical design, IMET for the validation of and calibration of photometers, ACTRIS, which is a European center for aerosol monitoring, both in situ and remote sensing, and we are involved in CARS, the Centers for Aerosol Monitoring. Of course, NASA in the frame of AeroNet network, because we provide the photometer, and the LabX Kappa for instrument synergy, so combination between different instruments. The main strategy that we have to try to classify and to identify particles is the combination between different instruments. And the main idea is that the more information we have, the more we can classify particles, we can type the particles. And so we have developed two different strategies. The first one, two different approaches, sorry. The first one is based on the existing photometers, the Cimel photometer, which equips the AeroNet network, yes, and the micropulse LiDAR CE710. And the combination of the two instruments is called the AMS Automated Aerosol Monitoring System, and this is what we push. So this system is based on the existing photometer instrument, and we can add a micropulse LiDAR. It's a two-wavelength LiDAR. The second approach is based on high-power LiDAR using Mie scattering, Raman scattering, and now the fluorescence of aerosols. And we will see the difference between the two systems, and that's it. Just an example, so for the first approach, I just said that we combined photometers and micropulse LiDAR, so here are the information on the photometers, the AeroNet photometer provided by Cimel. For aerosol study, we have mainly two different systems, the standard system, the TS9, and the TP9 for the polarization measurement. And they have the same wavelengths, except that the TP9 has polarization measurement. And you can see on the bottom left an example of Audi data here in Riyadh Airport in 2023, so that's an AeroNet data. And on the right part of the picture, you see the calibration center facility in Goddard at NASA Washington Center. For the first approach, we combine with the micropulse LiDAR. We have a set of different versions of this LiDAR, but the one dedicated to aerosol measurement is the GPN version. It contains two laser systems, so 532 nanometers and 808 nanometers. And the system is a micropulse system, so very low energy, continuous measurement, 24 hours a day, 36 all year long. And for difficult environment, we can also provide a thermal enclosure that can work between -30 up to 55 degrees. And if we look at the AeroNet network in the local scale and regional scale, you can see on the left picture that there are quite a lot of photometers, AeroNet photometers. And if you look at the local scale near Saudi Arabia, you see still there are some photometers, and one of the first approach will be, for example, to add some micropulse LiDAR here to be able to combine the data. And combining the data means getting some what we call a quick look like this. This is a quick look obtained in Lille, in the north of France, for 1 week, so it's continuous monitoring, continuous acquisition of the two systems. And just on post-processing, what you can get is you can identify cirrus cloud, saran dust, indoor pollution, urban pollution on the right, also aerosol volcanic ashes. This is just on 1 week acquisition data in Lille. So there are a lot of information when you start combining photometer and LiDAR system. The standard output is listed on the bottom, so we have the range corrected signal, depolarization at 532, extinction and backscattering coefficient. And if you go a little bit further, combining the two wavelengths of the LiDAR, you can get what we call a color ratio or vertical profile of angstrom exponent. And also, if you have you make some assumption on the aerosol density, then you can get the PM2.5, PM10 concentration, also separate in fine and coarse mode concentration. That's what we can get on post-processing. But you can also do this in live scan, so continuous running, the data are acquired continuously, and you get this kind of software acquisition. This is our software. So on the top, you have the extinction profile given by the LiDAR at 532 nanometers. On the bottom, you have the aerosol optical depth at different wavelengths. On the bottom, complete bottom, you have the water vapor content given by the photometer analysis. And combining these with the volume size distribution given by IRNet or given by GRASP, because we have GRASP inside the software, you can get on the left, top left, an example of PM10 concentration vertical profile. That's a continuous live acquisition, so that's quite amazing. Now, if I switch to the second approach based on the high power LiDAR, so here we are talking about Mie scattering, Raman scattering of molecules, and also what we recently added is the fluorescence of aerosols. And we are fully following the ACTRIS mandatory requirement and even going beyond that. So of course they ask for 3 wavelengths, for 355, 532, 1064, depolarization, so we can provide all this. The height resolution is supposed to be less than 50 meters, but we can go to 3.75 meters. Even it's not very important. And about the features, we satisfy most of the features recommended by ACTRIS. Talking about the instruments, the laser source, now we need power, so we need high power laser. Our suppliers is Lumibird Laser. It's a French company based in the south of Paris, and we are using either flash lamp laser or diode pump solid state laser. What is important to get enough signal in the fluorescence of the aerosol is to have energy. So we put, for example, a 260 millijoule, 100 hertz diode pump solid state laser that can emit this energy at the 3 laser wavelength, 355, 532, 1064. So that's a lot of energy. The consequence of this is that for the beam expander that collimate the beam, we have to separate the UV channel and the other channels. So that's an example of the 3D design. Another point on the instrument, so it's a telescope, a 40 centimeter diameter telescope, so you can get a lot of signal back. It's a cardboard made, so it's a really rich instrument. And for the analyzer part, the idea was to have a kind of Lego structure. So we have a unit cell where you can put anything, a filter, a beam splitter, anything inside, and the user can set up its own design to get up to 15 different channels. So I recall you that we can emit 3 laser wavelengths, but we can get up to 15 channels, including Raman and fluorescence channels. That's what I'm going to show just later. This is, for example, one of the many examples that we have of these instruments. So we have Mie and depolarization channel at 355, 532, and 1064 nanometers channel. So it makes already 6 channels. We can add the Raman, both vibrational and rotational channels to get the extinction and the backscattering coefficient. And then what we recently add is the fluorescence channel. So we have a long list of fluorescence channels. And you have an example on the left of one of the designs that we can make. So the strategy about this fluorescence is that we need to measure the fluorescence. And you have an example of on the left side of the shape of the fluorescence signal. So we all know about the Mie profile, the Raman profile, the efficiency of that. But if you look at the fluorescence, it's even less. So what we call the fluorescence capacity is much lower than the elastic one. So this is, and if you look at the spectrum, it's very large. So in a short bandpass filter, you need a lot, you need to have a lot of energy for the laser to be able to measure something in backscattered. And this is what we define the fluorescence capacity. And you see that it's a ratio between the fluorescence and the elastic. And you see that it's in the order of 10 to the power -4. So you need a lot of energy, and so you need a big LiDAR. But what is interesting, and this is the main slide of my presentation, is that we can do typing using the fluorescence, because every aerosol emits fluorescence. Whatever the type it is, it has fluorescence. So one of the examples is a paper published by Igor Velezovsky, which is in the team, is that just using the depolarization at 532 and the fluorescence capacity, we can do identification of the particle. And you see on the right side that the particle deposition versus the fluorescence capacity. And there are areas where it's only dust, pollen, urban, and smoke. Of course, you can mix that. But we can do identification just using this LiDAR and the fluorescence. Another example by Igor Veselovsky is this. So we developed this quick look analysis software. And there are 4 examples in Lille, north of France, where we have events containing smoke and urban, smoke and pollen on the September 2020. And on 2022, there was a combination between dust, smoke, and urban pollution. So we can do this almost in live mode right now. Another thing that we have done very recently is published by Igor Velezovsky too again, is that we have shown that some of the measurements published in the literature about water vapor measurement are wrong, because, as we said before, the fluorescence exists. All the aerosols emit fluorescence, and some of this signal is detected in the water vapor Raman channels. So if you're not able to correct this, you may overestimate the water vapor content that you have in the atmosphere. So this is a optical design that we have done to separate the contribution of the water vapor and the fluorescence in the water vapor channel system. So the main idea is to use depolarization, because the depolarization of water is completely different than the one of the fluorescence. The fluorescence is much bigger. So we can separate and get the real water vapor content. The next step, this is something that we're looking for the future, is now to try to combine the high power LiDAR that I've just shown and also the multispectral measurement given by the photometer. This is something we are working on, and we will rely on GRASP software to do this. The goal, of course, being to get the vertical distribution of particle concentration, but by type of particle. That's the goal, what we want to do. Thank you for supporting.